I am the virtual teacher at Egnatia Career College. Today we'll teach Orienting the drawings, fire-rated and acoustical considerations, seismic considerations. This is video number 8. Multifamily construction, urban courts. All architects use drawings to communicate their designs to those who must review them and those who will bring the design to live. Not all architects do this in exactly the same way. Some architects and drafters organize their drawings differently. And some construction projects call for communicating different kinds of information. Part 3 provides you the opportunity to see some variations in how architects present information on drawings and in styles of construction. The urban courts are one of the 3 housing styles included in a large development. The urban courts drawings were selected for reference in Part 3 because they represent quality construction. In a region where many construction practices and architectural styles are different from those in other parts. The courts have multiple floor levels and provide homes for 2 families in a single building. A complete set of drawings for the urban courts is far too large to include in the drawing packet that accompanies this textbook. The original sheet numbers have been retained, so the sheets in your packet are not numbered sequentially. As you work through the units of Part 3 and the corresponding drawings, take the time to understand all the information about a particular building feature and study all the drawings related to it. Orienting the drawings. After completing this unit, you will be able to perform the following tasks. Explain the information found on a typical cover sheet. Locate a particular building or plan within a large development. Visualize a building design by reading the drawings. Organization of the drawings. The drawings for a single or multifamily dwelling include many sheets. Some of the drawings are produced by the architect or the architect's drafters. Some may be produced by an engineer's office, and others by a specialty contractor, such as fire protection, plumbing, etc. Leafing through the entire set every time you need information from a particular drawing would be time-consuming and confusing. Architects follow similar pattern in organizing their drawings. The general order of drawing sheets is similar to that of specifications. Site plans are first. Foundation plans and floor plans, next. Building elevations, third. Then structural, mechanical, next to last. And electrical, last. The cover sheet usually includes an index or table of contents for the drawing set. The drawing set for urban courts is too many sheets to include all of them in the drawing packet with this textbook. Only the sheets that are marked with an asterisk in this figure are included in the packet. The complete cover sheet is included in the drawing packet with this textbook. Notice that some of the listings for some of the sheets are encircled with a scalloped line. These are sheets that were modified after the original drawings were produced. A small, numbered triangle matches numbered triangles found in the title block of the drawing. The same technique, enclosing in a scalloped line or cloud, is used for revisions to the drawings themselves. Some other useful information shown on the cover sheet for the urban courts are: symbol legend. Explains the symbols that are used for sections, elevations, keynotes, explained later, and revisions. Graphic legend. Explains the symbols used in this drawing set. Some may be conventional symbols used throughout the industry and some may be peculiar to this drawing set. Abbreviations. Some of these abbreviations are customary throughout the industry. Some customary in the region in which this work is done. And some may be peculiar to this drawing set. Without this index of abbreviations, some such as the difference between P/L and PL might be confusing. Project team. It is sometimes helpful to know how to contact a particular member of the project team when a question arises about a confusing detail or an apparent conflict. The workers on the job site should go to their foreman for such questions. The foreman should go to the superintendent if necessary. And the superintendent might go to the appropriate member of the project team. Identifying buildings and plans. Multifamily dwellings are often built in large developments, with many similar buildings in a single development. Some developments are completed in phases. One phase is completely constructed and begins earning income for the developer before the next stage is started. This figure shows the site plan for such a development. This project is to be developed in 4 phases. Each phase is outlined with a heavy broken line on the site plan. The first phase of the development includes 11 buildings. Each building is labeled as to building type and the parts that make up the building. Building type 2 is made up of 4 separate units, each with its own floor plan. Each unit is built like a separate building joined to the next. Each plan is identified by a letter or letter and numeral. The term plan is used to refer to a particular arrangement of rooms or design. This should not be confused with the use of plan to refer to a type of drawing. The plans in Building 2 are A, B1, B2, and AR. Each plan type is described on separate drawings. One technique that is used to create similar, yet different, plans is to reverse them. A reversed plan is created by building the plan as though seen in a mirror. The reversed plan has the same features and the same dimensions, but their arrangement is reversed. In Building 2 of this development, the south end is a reversal of Plan A. This is designated on the site plan and in this figure as AR. The letter R indicates a reverse plan. One way of reducing the impact of housing on the environment is to increase the housing density in a development. Moving people closer together leaves more space for the unbuilt environment. Many zoning ordinances require housing developments to include a certain percentage of green space. Housing density can be further increased by the use of multifamily buildings. Also, because these dwelling units share walls and have fewer exterior walls, they tend to be more energy efficient. Visualizing the plan. The first step in becoming familiar with any plan should be to mentally walk through the plan. This technique is described in Unit 18, for the lake house. Refer to the urban courts drawings as you mentally walk through Building 1. The first floor plan on sheet A3-1 shows 3 options for the entry area. They are elevations A, B, and C. This architect refers to optional designs as separate elevations. This study will focus on elevation A. Enter through the door at the lower right corner of the first floor plan. On your left are 2 doors. One into the garage for Unit A, and one into the garage for Unit B. There is an overhead door at the far end of each garage. The 2 side exterior walls are drawn with a material symbol that we have not seen. They have references to Keynotes 5 and 25. Keynote 5 indicates that these are stone veneer walls. Keynote 25 tells us that they are 1-hour rated fire walls. The interior wall separating the 2 garages is also a 1-hour fire wall. But in this case, we know that because of the symbol used to draw the wall. That symbol is explained on the cover sheet. Straight ahead of the entry door is a stair to the second floor. Go to the second floor plan on sheet A3.2. At the top of the stair, there is a window onto the balcony and an entry door into Unit A. To the right, as we enter the unit, there is a living room with 3 windows in the back wall. To the right of the wall with windows is a door onto the balcony. Walking back through the living room, enter the kitchen area. Between the kitchen range and the refrigerator, you enter the master bedroom suite. Notice the notation in the opening indicating that there is a soffit overhead. Just before you enter the suite, immediately past the soffit is a coat closet on your left. The bedroom closet is on your right. Continuing past the closets, there is a passageway on the left. On the left as you enter the passageway is the laundry with a washer and dryer. Straight ahead is the master bath, with a vanity on the right, a shower straight ahead, and a separate toilet room on the left. Return to the stairway and climb the stair to a landing where the stair makes a U-turn and continues up. Now refer to the third floor plan on sheet A3.3. At the top of the stair, the Unit B entry is on your left. Inside the door, immediately on your right, is a coat closet. Past the closet, turn right into the master suite. Straight ahead, on the rear wall of the building is a closet. On the left is the master bedroom. There is a sliding barn door inside the bedroom. Opposite the bedroom doorway is the bathroom door. Inside the bathroom there is a toilet on the right, a vanity on the left, and a shower straight ahead. Back out through the passageway and enter the kitchen area on your right. On the left is a storage closet. The kitchen has an island sink and cabinets and appliances on 2 walls. Beyond the kitchen is the living room at the front of the building. Turn left at the front wall of the building into a passageway with the laundry door on the left. Beyond the laundry room is a stair leading up. Refer to the 4th floor plan on sheet A3.4. The stairs lead up to a loft, providing more living space. There is also a storage area. On the left wall of the loft is a sliding door onto the roof deck. The roof is sloped 1/4 in 1 foot. But that is gradual enough to allow for outdoor furniture. 2 sides of the roof deck are open but protected by a railing. Described in Keynote 17. Fire-rated and acoustical considerations. After completing this unit, you will be able to perform the following tasks. Identify and explain the construction of fire-rated walls. Find and interpret detailed information on acoustical considerations in walls, floors, and ceilings. Introduction. Multifamily buildings are constructed the same way as single-family buildings in most respects. A wall that is shared by 2 living units in a multifamily structure is called a party wall or common wall. In addition to the usual requirements of a wall, a party wall provides more fire resistance and sound privacy. When 2 living units are separated by a floor and ceiling, that construction needs to provide the same protection a party wall would provide. Fire-rated construction. Fire-rated construction serves 2 purposes in the event of a fire. It slows the spread of fire, and it maintains structural support longer than non-fire-rated construction. Approved fire caulking or fill must be used at all utility-line fire-rated wall penetrations. The most obvious way in which a wall, floor, ceiling, or roof can slow the spread of fire is by having a fire-resistant surface. Plaster and gypsum wallboard are fire-resistant materials. They do not burn, and they do not easily transmit the heat of fire to the framing members on the other side. Unfortunately, standard gypsum wallboard breaks down and crumbles in very high heat. Fire-rated wallboard is used where a fire-rated wall is required. Fire-rated gypsum wallboard is Type X or Type C wallboard. Varying degrees of fire resistance can be achieved by using a second layer of fire-rated drywall on one or both sides of the wall. Other materials, such as OSB that has been treated. Fire-rated construction is frequently used to separate garages and mechanical rooms from living spaces. Party walls are also fire-rated to prevent a fire from spreading between housing units. To separate the housing units, a fire-rated party wall should extend all the way from the foundation to the roof. Most building codes allow an alternative to extending the party wall through the roof. The fire-rated construction may end at the bottom of the roof, as long as the roof is a fire-rated construction. This usually means that the roofing material resists fire for as long as the party wall does. For example, if the party wall is required to be a 1-hour code wall, it resists fire for 1 hour. The roof must be covered only with material that also resists fire for 1 hour. Fire-rated walls must also prevent fire from spreading vertically inside the wall. If left open, the spaces between the studs in a frame wall act like chimneys, allowing flame to spread very quickly from one level to another. To prevent vertical flame spread, stud spaces are not permitted to be more than 10 feet high. The spaces between the studs are closed off with fire stops at each level. Instead of wood fire stops, the wall cavity can be blocked off with fire-resistant fiberglass insulation. Openings are usually avoided in fire-rated walls. Where it is necessary to include a door, it is made of fire-resistant material. The fire rating of the door must comply with the building code. Doors in fire walls are equipped with a self-closing mechanism. Sound control in walls. To provide privacy between the housing units, common walls and floors should not allow the sound from one unit to be heard in the next unit. The measurement of the capability of a building element to reduce the passage of sound is its sound transmission classification, STC. The word acoustic is often used when talking about sound control. It simply means having to do with sound or hearing. Sound is transmitted by vibrations in any material, solid, liquid, or gas. To slow the passage of sound, a party wall must reduce the flow of vibrations. The materials used in the construction of most walls vibrate relatively well. Also, they transmit these vibrations to the air inside the wall. Sound can bend around corners and find its way through the smallest of openings. The air carries the sound to the other side of the wall, where it is transmitted to the air on the opposite side of the wall. The drywall joint between the wall and the ceiling may require sound deadening putty to prevent sound from passing through that joint. The electrical installer may be required to utilize acoustical insulation or some other sound attenuation material around flush device boxes. Raceways may require installations that reduce sound transmission, such as expansion joints, flexible raceway, or raceway offsetting through the party wall. The STC rating of a wall can be improved greatly by not allowing the studs to contact both surfaces. This may be accomplished in one of two ways. One method is to attach clips made for sound insulation to the studs and then fasten the wallboard to these clips. The clips absorb the vibrations. Using the clips and sound deadening fiberboard results in an STC rating of 52. An STC of 45 is achieved without clips by using 2x4 studs and 2x6 plates. The studs are staggered on opposite sides of the wall so that no studs contact both surfaces. The STC can be increased to 49 by including fiberglass insulation, separating the two sides of the wall framing on separate plates and insulating both sides of the wall cavity yield an even higher STC rating. There are many other products and designs that can be used to control the sound transmission through a wall. It is essential that those who assemble common walls understand and follow the architect's design. Sound control in floor and ceiling assemblies. The principles that are used to stop the flow of sound through walls also apply to the floor/ceiling assembly. But wall construction is different from floor/ceiling construction. Some provision must be made to either absorb or block the vibrations that are sound. The IRC requires an STC rating of at least 45 for common walls and for floor and ceiling assemblies. Another type of sound comes into play for floor and ceiling assemblies. When a person wearing hard-soled shoes walks across a wood floor, the sound created by the impact of the footsteps can be a real annoyance to those living in the rooms below. The acoustics industry has devised a system for impact noise insulation. The Impact Isolation Class, IIC, is a rating of the floor and ceiling assembly's ability to isolate the sound from footfall and other impact sources. The IRC requires an IIC of 45 or more for common floor and ceiling assemblies between dwelling units. A 45 IIC rated floor would not be satisfactory to many people. A rating of 65 would satisfy most individuals. There are so many options for floor surface materials, sound deadening products, and ceiling materials that it is not possible to list even the most common options here. For example, the floor and ceiling assembly shown in this figure would yield an IIC of 51 to 56 and an STC of 56 to 60. Keynotes. On larger construction projects, the drawings might become very cluttered and confusing to read if all of the information is drawn and described on them. Also, there can be multiple places where the same information applies. To avoid confusion, much of the information may be shown in keynotes. A numbered mark, in this case, a small rectangle containing a number, is placed on the drawing. A column of notes on the right side of the drawing sheet explains what each of those keynotes indicates. Seismic considerations. After completing this unit, you will be able to perform the following tasks. Identify the seismic design category for a given location. Explain how earthquakes affect buildings. Find information about seismic considerations on construction drawings. Where earthquakes occur. In some areas where earthquakes are a potential hazard, buildings in those areas must resist these seismic forces. Earthquakes are one of the three types of loads that buildings must support by providing load paths through the structure and back down to the ground. Dead loads. The weight of the building materials. Live loads. Loads that change or move around the building, such as people and furniture. Dynamic loads. Loads that produce varying amounts of force, such as snow, wind, or earthquakes. Seismic loads. Many of the methods used to resist earthquake damage will also prevent damage from strong winds. This chapter will concentrate on how buildings resist seismic forces and how to identify those design elements on construction drawings. The seismic design category map shown in 4 parts in this figure shows the seismic design standard for all areas of the country. The chart in the next figure describes the potential risk for each category. Forces created by earthquakes. The amount of damage done by a seismic event depends on several factors, including distance from the earthquake's origin epicenter, the strength and type of earthquake, site soil conditions, and the type of building construction. During a seismic event, several types of energy waves are introduced into the structure. These include forces that shake the building back and forth, like moving a dish of jello rapidly left and right, and waves, much like ocean swells that lift the building up and then drop it. The side-to-side motion can come from any direction and causes the building to sway, particularly on the top floors. The ground waves can also tilt the building as well, cause the building to lift off the foundation. Either of these forces can cause building floors to separate, the building to overturn, or the supporting walls to rack and fail. This racking would be similar to a freestanding row of books being pushed at the top edge until the row fell. To resist this damage, the structural drawings for a building that might be subjected to seismic activity specify methods to ensure that the foundation design addresses specific site soil conditions. The foundation will hold together as one structural unit. The walls will be securely attached to the foundation. The walls will resist racking and overturning. The walls and floors of each story will be securely attached to the story above and below. The floor and roof will lend anti-racking ability to the structure. These structural design features allow the structure to absorb the energy of the earthquake and provide a load path for the energy to travel back into the ground while leaving the structure intact. Soils conditions. The site requires a geotechnical soils report, performed by a soils engineer. This provides information on soil types, the strength characteristics of the various soils present, landslide potential, and any other geologically related hazards. Structures built on rock typically perform better than those built on soils, particularly loose soils. During earthquakes, some soils are subject to liquefaction, where the soil acts like a liquid, offering the structure no support. The geotechnical report addresses all these concerns and provides information on preparing the site for the foundation. The report also provides the structural engineer the site and soil information needed to design the foundation. Reading structural drawings. The structural drawings for urban courts that are included in your packet are 2 plan sheets, S7.1 and S7.2, and 2 sheets of details, SD1 and SD3. Familiarize yourself with the various views, schedules, and notes and how they are referenced in the plans. Note that most details on S7.1 will be found on SD1, and most details on S7.2 will be found on SD3. The foundation and framing plans have schedules, such as shear wall schedule, notes, such as general floor framing notes, and other miscellaneous notes. They also have other plan views, but are titled elevations B or C. Not to be confused with architectural elevations. Schedules use different shapes, such as triangle or 6-angle, to denote a reference to different schedules, just as in architectural drawings. The reference to details is the same as in the architectural drawings. A circle with the detail sheet number on the bottom, and the detail number on the top. Foundation. Concrete is a very durable material and a good choice for building foundations. But it does have one drawback. While concrete is very strong in compression, it is weak in tension. Looking at the profile or elevation of a slab, the forces placed on the slab tend to make it deflect or bend, causing a compression face and a tension face. Because steel has high tensile strength, steel rebar is added to the tension side of the slab, usually the bottom. This adds tension strength to the slab. To add even more strength to the slab on the urban quartz project, a process called post-tensioning is used in addition to using rebar. Post-tensioning involves the placement of a grid of plastic-coated cables in the concrete forms prior to concrete placement. Both ends of each cable penetrate the form and extend past the edge of the slab after concrete placement. Once the concrete is placed, the concrete is allowed to partially cure, usually about 7 days or until a specific compressive strength is achieved. One end of the tensioning cable is then anchored and a hydraulic tensioner is used to stretch the cable inside the slab. The plastic coating allows the cable to stretch inside the now solid concrete. The cables are tensioned to approximately 33,000 pounds. Specifications for the spacing and how much the cable will be elongated once tensioned are shown on Urban Quartz Sheet S7.1. Post-tensioning is similar to pre-stressed concrete beams used in highway bridges, and the result is the same. The cables are pulling the sides of the concrete slab together, and the slab gains a much higher resistance to tension stresses. Sheet S7.1 has a hold-on schedule, and this figure shows a typical hold-on assembly. Hold-ons are used to anchor the first-story walls to the foundation and resist the overturning forces discussed earlier. Hold-ons are manufactured in a variety of configurations. They can attach to a bolt embedded in the concrete or be set directly in the concrete. Usually they bolt to a post or studs in the wall, but can also be nailed to the post or studs. They are a critical part of the shear wall design. The other anchoring system is a series of foundation anchor bolts embedded in the concrete that bolt the wall bottom plate to the concrete. This resists both uplift and lateral displacement. Walls. Urban Quartz is a 4-story wood frame building. Wood is a very forgiving material in earthquakes. It tends to bend and return to its original shape. But that same flexibility makes it too flexible for very large or tall buildings. Any building in earthquake country needs to be braced to resist shear forces. Shear forces are those that move long walls or floors and distort the structure by racking. The standard shear-resisting method used for walls is to apply structural sheeting such as plywood or OSB, nailed to the studs, and plates in a prescribed manner. Because shear walls must resist the forces of an earthquake, the size, placement, and spacing of nails is especially important. In areas with very little seismic activity, it is not customary for construction drawings to specify nailing schedules. But in high seismic areas, nailing is typically specified by the structural engineer. Sheet S7.1 has a shear wall schedule. That includes information on sill plate thickness, nailing schedules, and whether structural panels are required on one or both faces of the wall. This schedule also calls out anchor bolt spacing and alternative connection methods. Notice the garage door openings on the bottom floor. Since the shear panels cannot continue across those openings, the narrow wall on one side of the opening is paneled each side and has heavy hold-downs tying it to the foundation. There is also shear transferred from floor 2 to the first-story wall. A critical design consideration is that the shear wall sections stack vertically. Upper-level shear walls occurring directly above the shear walls below. On sheet S7.2, there are references to strap hold-downs connecting each story to the story above, holding the building together vertically, and transferring shear from floor to floor. Details of these connections, including the straps, are included on sheet SD2. Floor and roof. An uninterrupted expanse of floor or roof sheeting creates a strong horizontal shear-resisting diaphragm that not only prevents the building from twisting or racking horizontally, but can also share its shear strength with the walls below. Shear transfer details are shown on sheet SD3. Also, detailed or drag collectors, reinforced floor, and roof members that collect both tension and compression loads from walls and transfer them to the roof or floor. These are particularly necessary where there are reentrant, inside, corners, or other discontinuous load paths in the walls.